What I'm going to talk about today is a bit of a brief overview of recent work we have been doing around combining human intelligence together with machine intelligence, and I will talk about a few of the challenges that happen that you need to deal with when you build such systems, with a specific focus on bias. And I will try to give several examples of bias in this type of systems, and hopefully provide some suggestions on how to deal with it. But really what I want to give you, have you leave from here, is a list of open questions and topics for you to work on. Okay, so this is a brief, a big picture of the type of research my group is doing. It all started building information retrieval, information access systems, where we looked at accessing information through entities rather than keywords and just text and words. So really building systems that can present information around entities such as persons, location, and organizations. And then when building these systems, we started to look at the human in the loop approach. So again, combining humans and machines together in order to get the best out of the two worlds. And when doing this, we realized a lot of the challenges that are created when you have humans in the loop. We look at how to make crowdsourcing platforms better. We look at human factors in crowdsourcing platforms. And more recently, a lot of questions on data quality, which relates to the bias created by humans annotating data and then reflected in artificial intelligence models trained on top of this data. So out of all this, what I'm planning to talk about today is, in the first part, really, as I said, give you a few examples of bias in crowd-generated data. So when we collect manual annotations at scale from a large population of human individuals, what type of bias do we encounter there? And then in the second part, I will talk about interaction behavior data and how we can use that to better understand the population of individuals annotating data. And again, how can we use this data and models to improve the conditions of the working condition for the human annotators, but at the same time to improve the quality of the data that we are collecting from these human annotators, and then we are training supervised models with. Okay, so let's start the story with crowdsourcing. In my opinion, the key open challenge of collecting manually labeled data by means of crowdsourcing is that of quality control. So making sure that the data you get back from a crowdsourcing platform is of high quality. And today, I would argue that the most popular quality control mechanism is the use of gold question. So this means that if you show 10 questions within a task to a crowd worker, 1 out of 10 is a gold question, which means you know the correct answer for question 7, but you don't tell it to the workers. You let the workers answer all of 10, and then you check if they answer correctly question 7. If they did, you trust that all the other 9 are good quality. If they make a mistake on question 7, you throw away all the other answers. So this is one way, because you assume to only have very few gold questions, because that require expert manual annotation, and that's very expensive. And the entire idea of crowdsourcing is to scale up the data collection. So the assumption is that you have very few gold questions. The other requirement here is that the crowd worker doesn't know which of the 10 is a goal question, because if they knew, obviously they would only focus on the goal question, answer it correctly, and the others, they can answer it randomly because they are not checked on that. So because of these properties, what you can do, or better, what can a group of workers collaborating together do, is basically share information and data about which questions they are observing. So imagine a browser plugin that is sending all the questions observed in crowdsourcing tasks to a server. This server is collecting frequency information for questions, how often they appear, and then sending back this information aggregated to each individual worker by signaling which questions are likely to be gold. So how this works is based on the frequency, right? We said gold questions are very few compared to the entire set of questions, and this means they will need to appear much more frequently than any other question, the non-gold questions. If we look from a real data set, how often gold questions are being shown to crowd workers as compared to the non-gold questions, it's very easy to distinguish, right? As soon as a question is observed more than 10 times by different workers, that's very, very likely to be a gold question, and the system can highlight them to workers, and now workers can only focus on the gold questions and become more efficient, make more money per hour, increase their earnings without necessarily providing the data quality that the requester requires. So this is very interesting, right? It's exploiting a statistical feature of the setup, these gold questions appearing much more frequently than the non-gold questions. So note that the non-gold questions will still appear more than once, right? It's common practice to assign a question to multiple workers and then aggregate their answers, but still, when we compare frequencies of questions, it's very easy to differentiate the gold and the non-gold questions. So what this means for workers, as I said, is that they will save time. The purple line here on top is the time it takes workers to complete a specific task in general when they don't know which questions are gold and which are not. So they just need to complete the answer correctly at the best of their abilities, all the questions, all the tasks. And the green line shows what happens if they are using the gold question detection approach that I explained. You see the time it takes them to complete the tasks significantly decreases the more work is being done, right? Because the more work this group of workers are doing, the more data are sending to the server, and the more accurate the estimation of which question is gold becomes. So the more accurate gold question estimation they have, the faster they become, right? They can only focus on those highly likely gold questions and no need to focus on the other type of questions. So this is a very interesting approach, right? It makes workers, in a way, attack probably the most popular quality control mechanism that we know today in crowdsourcing. And while there are some countermeasures to this attack that requesters and platforms can take, what is actually more interesting is not really starting a fight between workers and platforms, and the platform responds to the worker attack and workers then adjust to that. So rather than going in that direction, it's probably more interesting to think at different type of quality assurance approaches, including building trust relationships between the platforms and the workers, where workers can be trained over time and really have an increasing earning prospects over time and possibility of career and so on, as it has been suggested in the literature. But let me go back to the topic of this seminar, which is a bias in these type of systems. So where does the bias play a role here in such a scenario? Well, if we do have a group of colluding workers using such an approach, we have seen that the time it takes for them to complete tasks significantly decreases. So what this means in a crowdsourcing setup is that this group becoming more efficient and faster not only will make more money as compared to others who are not using such an approach, but at the same time, because they are faster, they will complete more tasks, make more money, but also contribute more labels to the dataset collection process which is happening through the crowdsourcing platform, right? So this small group of workers will complete a large part of the tasks in the crowdsourcing project, and therefore will dominate the labels present in the final data set, right? So there is this bias due to such an attack approach that will basically make it happen that the vast majority of the labels are contributed by these very few workers working in coordination. So this is the first example of bias, which is created by a specific attitude or approach of a small group of workers in the crowd. Let me now move to another example, which is knowledge graphs. We are still talking about crowdsourcing, so it's a crowdsourced knowledge graph, but here the incentive is not anymore monetary, it's not financial. Rather, these contributors are editing a knowledge graph on a voluntary basis. We are talking about Wikidata, which is one of the Wikimedia Foundation projects, and it's very similar to Wikipedia in the crowdsourcing aspect. The only difference is that instead of editing articles, editors in Wikidata are editing a knowledge graph. So they are adding entities, they are adding relationships between entities in the graph, and they are modifying what is already there, right? So they could modify existing relations or modify attributes of an entity in the graph. What also I find interesting of this graph is that it's evolving over time, right? A bit like Wikipedia, new nodes are added, new edges are added, so it's a graph, a very large graph, which also evolves over time. So what we did in this piece of work is we look at 4 or 5 years of edit history of the graph, and we have seen not only how the graph evolves over time, but really what makes editor contribute for a long period of time, several years, as compared to those who don't contribute for a long period of time, but stop relatively early. So they do a few contributions, but then they don't do it anymore. So we look at what makes some editors contribute for a longer period of time as compared to others, and a few observations we have seen by looking at data, by running surveys and talking to them personally, is that they manage to make it an habit. So for example, they will find a routine in which every evening they will do some edits, or every weekend they will dedicate a couple of hours, contribute to the project. So they manage to have a continuous contribution, which is regular over time. Also, they try to diversify the activities they do in Wikidata. For example, first they focus and try to include all the mayors of all the cities in Germany, and then once they have done that, they will move to something else like butterflies, and making sure that there is all the relationships to butterflies in the graph. So by diversifying, they are able to expand their lifespan in the project. Again, let's go back to the bias question. What's the bias issue here? Is that, again, like before, these long lifespan editors, they will dominate the contribution to the graph. So they potentially create, because they contribute much more than others, like in the previous example, they may create a bias in the type of data present in the graph, right? Because the graph is evolving over time and it's actually expanding over time, what we will see is that the graph is not complete in any given point in time, and what is there and what is not is mainly decided by this very small group of people who dominate the contribution in the knowledge graph. Okay, so we have been talking about knowledge graphs, crowdsourced knowledge graphs which edits are dominated by just a few editors. This is true not only in knowledge graph, in Wikipedia as well, and in other crowdsourcing projects as well. But let's stay on knowledge graphs and look at this problem of completeness, right? Completeness is one of the data quality dimensions that we need to look at. So we need to make sure the data we use is complete. When we talk about knowledge graphs, one question is the graph complete, right? Specifically with an example, do we have all the cities of Germany in our knowledge graph, right? Or we are missing something. So in order to answer this question, do we have all the entities of one type? What we need to do actually is to know what's the class cardinality, right? Our class is cities of Germany. We need to know the cardinality of that set. That is the total number of cities in Germany. If we know that number, then we know what's the level of completeness, right? An easy example is US states, right? We know the class cardinality of US states is 50. If we have 45 US states in our knowledge graph at the moment, we know that the completeness level is 90%. So the problem of knowing how complete is the graph today really boils down to estimating the cardinality of a class for entities in the graph. So that's the interesting and challenging problem, right? How many cities of Germany are there in general? How many US states? So while these are easy classes to know the cardinality for, there are others which are more difficult. For example, here, paintings by Vincent van Gogh. So what we want is to, by looking at the knowledge graph and how it has evolved over time, we want to estimate the cardinality of a class. That's the problem. What we did is we used statistical methods from computational ecology that is estimating the cardinality of classes. So the original example is, if you want to know how many lions there are in the savannah, what you do is you go to the savannah, you start to capture some lions, you tag them, and you let them go. Then after a while, you capture again another group of lions, you tag them, and you let them go. By doing this, when you recapture lions that you have tagged previously, by measuring how many new lions and already observed lions you capture each time, you are able to estimate the total number of lions in the savannah. So we apply that idea to entities in Wikidata, and we do the following. This is the edit history of Wikidata, and we start to observe entities, in this case for the class monument. So we start observing entities, different type of entities appearing in edit history in Wikidata over time. And then for entities of one class, we use these occurrences, these observations, in order to estimate how many monuments there are there. And here we show over time, again, over the number of observations, how different estimators estimate what's the cardinality of the class for the entities we have observed. And you see that after enough observations, these estimators actually converge to the right number, to the right cardinality. So apparently there are around 850 paintings by Vincent van Gogh. That's our ground truth. And the estimators are able to estimate that precisely after enough observations of entities in this class. Okay, so let me move to another domain in which we use crowdsourcing, and again, where we observed a bias problem. Here the problem, the task is truthfulness judgments. So we are asking crowd workers to tell us whether a statement, a piece of news is true or not. This is, generally speaking, a task which is done by expert fact checkers that follow a forensic process. And the question we had is, can the crowd do the same, right? Can we get 10 crowd workers to tell us whether a statement done by a politician is true or not? And then we can measure their accuracy against the experts. We have done this on different data sets, from the US and from Australia. We use different scales to collect these labels. Anyway, long story short, this is one plot that is basically saying that yes, it works. If we compare the labels, the truthfulness labels provided by crowd workers that you have here on the y-axis, to the truthfulness labels provided by experts here on the x-axis for two data sets, the US dataset and the Australian dataset, you see that there is a correlation, right? For different levels of truthfulness, here on the right, top right, you have the most truthful statements, and here on the bottom left, you have the extremely fake statements. You see a correlation, right? You see that when you aggregate the answers from the crowd, the trend is the same as the one the experts, right? All the statements at all levels tend to be to get a higher score from the crowd when they get the higher score from the experts. So the short conclusion is that it is possible to scale up the collection of fake news judgments by means of crowdsourcing. But let's talk again about bias, right? That's our main focus for the day. When we do this task of manual labeling fake news, what is interesting is that, again, there is a bias in the labels we collect, in this case, again, by means of crowdsourcing. So what we did is, again, our question was, can crowd workers do the same as expert fact checkers, at least in the classification step? And the answer is yes. But on the other hand, when we start to break down the labels we collect from the crowd, we see that there is a political bias, right? We have seen that if you get a crowd worker who self-reportedly voted Republican at the last election, and you show them a statement from a Republican politician, they are going to believe to it significantly more than other workers. So this is shown in this plot, right? Again, on the x-axis, you have the expert labels from true, extremely true to extremely false. And on the y-axis, you have the crowd worker labels. In this plot, you only see statements by Republican politicians, so the red politicians, and you see that the points in red here, which represent crowd workers who voted Republican, the blue dots represent crowd workers that voted Democrats the previous election. You see that at each level of truthfulness, the red workers have a significantly more positive value towards these statements that are aligned with their political thinking, right? For red politician statements, red crowd workers are much more generous than the blue crowd workers. If you switch parties and colors, you get the same phenomenon. So again, the conclusion here is that when the political background and thinking of the human annotator is aligned with that of the content, they are much more lenient in their judgments. If it's the opposite political party, they are much more critical in judging truthfulness. Again, a very interesting observation about the bias in the labels we collect. And then remember, with these labels, we typically train supervised models to do automatic fake news classification. So what this means is that depending how we collect the label and who is providing the label, these supervised AIs will perform significantly differently, right? So here the message is, it is very important to make sure that not only you have all the quality control mechanism in place, but also you carefully select the group of annotators who is generating the manually annotated data, because again of the bias effects that are reflected in the data and therefore in the models we train with the data. Anyway, I'll come back to this observation. Let me now move to the second part, which is about observing user interaction behaviors and a couple of examples of what we can do with it, with this type of data. So the type of data I'm talking about is really the type of data you can collect at the low level. Think of every mouse clicks, keystrokes, keyboard shortcut, Control-C, Control-P, scrolling a page in the browser, opening a new tab in the browser, all these type of low-level actions that it's possible to log in a very simple way, actually. So this represents a crowdsourcing task, but actually can be any HTML page which is available on the web. In this page, it is possible to embed some JavaScript code which will not change the way the page is presented to users in browsers and mobile phones. But what this JavaScript code does is that at every of these actions, it's sending some message to a server which is storing all this data. Basically, every time a click is done or something is typed into a text area, the JavaScript code will send all this information to a server. So that's the setup I'm considering here. Let's see a couple of examples on why this data is useful. So looking at the crowdsourcing example, right, we have crowd workers completing tasks and sending these labels back to the platform and then to the requesters who are paying for the labels. One thing that happens is that, as we have seen in the first slides, right, we might have 10 questions that workers have to answer to complete a task. So here are represented by n steps. What could happen is that a worker starts working on a task, and then at a certain point during the task, before reaching the end of the task, they decide to stop, to drop the task, to abandon the task, as we say, and then go back and look for something else. If they do this, what happens is they actually losing money, right? They started some work, they completed some work, they invested some time, but they will only get the reward, the money attached to the task, if they completed the task and sent it back to the platform. Otherwise, all the work they have done is lost and gets unrewarded. The data they have created is lost, it doesn't go back to the platform, and they don't get rewarded for that work. So the first question we had is, how big is this phenomenon, right? We didn't really know what happens, because as requesters and even as platforms, you only see the tasks that are submitted to the platform, and then you can decide whether you reward them or not, but we never see what happens before they submit the task, and we don't know how many start but don't finish. We, again, did a large data collection effort, and what we observed in our experiments involving a large number of workers and tasks, that still a lot of time is wasted on these tasks and it's not rewarded, right? Because the worker decide not to complete the task, not to submit it, they abandon the task, and therefore a lot of time is wasted by the workers and is not rewarded the platforms and the requesters. So it's a huge phenomenon, and again, we didn't know about it until we actually ran an experiment in which we were able to observe, right, thanks to this logging embedded in the task, what workers are doing before completing. So this is the very first question we wanted to answer. How many finish, how many don't, and when they stop in the process. Another interesting question that we can answer thanks to this type of interaction data is how different crowd workers complete tasks differently in the platforms. So what we did here is we used the different research approaches. We collected this behavioral data, but we also, again, talked one-to-one to crowd workers to understand their strategies and their ways to complete tasks on crowdsourcing platforms. And really, we wanted to compare crowd workers with a lot of experience, several years of experience, with those who have very little experience. And again, looking at the behavioral data, the interaction data that we collect, we have seen that experienced crowd workers do tasks very differently from non-experienced. One assumption we had is that those who are very experienced would use shortcuts, keyboard shortcuts like Control-C, Control-V, or Control-F to find keywords in the task to make the task completion process faster. Well, what we observe is that while Control-F is not very popular, copy-paste is very much popular. They reuse a lot of the text they originally generate first, and then they reuse it later on and they modify it quickly in order to, again, reduce the time it takes for them to complete the tasks and therefore to increase their hourly wage because they are rewarded on a per task basis. So the more tasks they complete in an hour, the more money they get in that hour. So a few observations when we compare the very experienced workers with the novice workers is that there is a lot of text reuse to make task completion more efficient. They are faster, which again makes them do more money, and that makes them stay in the crowdsourcing environment for a longer period of time. The quality, when we compare the quality between the experienced and the non-experienced, is not significantly better. Again, the experienced workers are just faster than the non-experienced ones. And this creates a bias again, a bit like we have seen in Wikidata, a bit like we have seen with the gold question attack. These experienced workers, because they are faster, they end up completing more tasks. On the one hand, because they are there for a longer period of time, the experience, and on the other hand, because they are more efficient, right? In 1 hour, they will do many more tasks than those who are newer and slower. So what this means for AI researchers who are collecting manually labeled data to train their models is that a large portion, if not the vast majority of the labels that they collect through crowdsourcing platforms is contributed by these experienced workers who are not necessarily providing better quality labels. They are just, again, dominating the contributions to the platform, to the data set which is being collected. Okay, so the last example I want to show you on how to use this behavioral data is to create models of behaviors, of user behaviors. So what we did in this work is, again, we took this action logged by having crowd workers or web users interacting with some online content, and then out of these single actions, which actually happen as a sequence over time, as an interaction sequence, we generated n-grams of sequences, for example, Ctrl+C, Ctrl+V, of frequently occurring sequences or n-grams of actions in our dataset. So if you are familiar with natural language type of data, you see that this is something you would typically do on documents and words and tokens. And indeed, this is what we did. We applied a very common technique, which is that of word embedding on this type of data. And what we did is basically, we are able, thanks to this word embedding idea, is to generate representations of user behavior data as vectors into a vector space. So now, thanks to this, what we have is a vector space representation of users and their behaviors. And this allows us to, for example, compare different users and their behaviors. For example, we have seen the groups of very experienced and not so experienced workers. We can see how their behavior in the space representation is placed and whether they are in the same place or not. Also interestingly, again, these actions happen over time, so we can see at how behavior is changing over time. We can look at one, say, Wikidata user that is contributing over 5 years, and we can look at their behavior in the first year and then how their behavior representation changes year after year. Right, so we did this type of study, and again, just to show you a couple of pictures, this is the type of representations that you get, right? Here on the right side, you have a two-dimensional projection of this multi-dimensional embedding space. But even in 2 dimensions, you see some interesting patterns, right? Here we are looking at Wikidata editors, and the blue ones are the ones who are less active. They have a short lifespan of contribution. The red ones are the ones who are very active and have a long time span of contribution. So what we see here is that the blue ones have most of them have a very similar behavior pattern in this space, while the red ones are spread around the space. So what this means is that those who stop contributing, they all have a very similar pattern, behavioral pattern that leads them to quit the project. While the red ones all find different ways to, again, find a way to contribute more, but in different ways. So there is no one way, one path to success, but there is one common path to failure. Here on the left, you have a crowdsourcing task, which here now we are looking at this vector space which contains different things, right? We are looking at the sequence of behavior, Ctrl+C and Ctrl+F here, which is close to a task duration of 24 seconds. Here you have other task durations of much higher, of 200 seconds, 100 seconds, 100 seconds. So 24 is one of the faster workers, and you see that they use a lot of Ctrl+C and Ctrl+F shortcuts. And these, again, they are closing the space. It makes them faster when using these. Those instead who do a lot of changing radio buttons in the task, they are much slower, more than 200 seconds. So again, not surprising findings, but again, this vector space representation really allows to find patterns and similarities between behaviors and between different groups of users, of workers, depending what the user behavior data set is. Okay, And with this, I'll finish my overview of a few of recent work we have done. I want to go back to the problems, right, that we talked about. We have talked about manually labeled data collected from humans by means of crowdsourcing or in other forms, which comes with some bias. And I give you some examples. So now we have all these manually labeled data set, which we typically use to train supervised models that come with some bias from the humans who have been creating the data. So this bias will then be reflected in the AI we train, and then will be presented to users that also come with their own biases and stereotypes. We have seen the political bias example, right? We have seen that if we show in, say, search results or information systems, recommender system outputs, something which is aligned to the user political, in our example, background, they will appreciate more than others, right? So the question now becomes, what should the system do when the data which is coming in input is biased and the user which is coming to interact with this data is also biased? What is the best way for a system to manage this relationship with the user, right? We know that web-based commercial internet companies, they all optimize for user engagement. So that implicitly makes the content to be aligned with the user bias, right? Because that increases the time spent by users, increases the number of clicks, increases the number of ads we can present, the products that users buy, the movies they watch. So all this reinforcement is due because of the metrics that internet companies are optimizing for. So that's my first question without, without an answer. Let me also talk about a few other open directions, in my opinion. So what we have seen today is several examples in which we can rely on crowd workers to provide manually annotated labels, which are not perfect, but of good quality. We can rely on supervised models to provide very efficiently classification decision at scale, but again, still with some errors. And we have seen that experts also provide very few, very inefficiently high quality labels and explanations why they provide such labels. So another question is, how do we combine all these different agents together in order to build a hybrid system that, again, gets the best, right? The best out of all these things, the scale of human annotation, the speed, efficiency of machines, the quality and accuracy of expert scrutiny of the data. So related to that, a few questions: who should do what? When we need to allocate the labeling tasks, who do we allocate it to when we have experts, non-experts, automatic systems? Can we combine them together, right? Once a president is tweeting something, can we have an AI real-time labeling it in true or false so that people can be alerted with something at the bottom of the tweet? And then later, maybe 24 hours, 48 hours later, expert fact checkers can slowly expand this automatic classification with many more details and background information. Which ones, which tweets, which statements are more urgent than others to check? Can we prioritize automatically these for experts to do? Can the crowd help prioritizing and identifying which ones should be fact-checked first in a fake news scenario, and so on, right? So how do we get these systems in place so that also experts, in a way, are able to work with them in a way that they never done before, right? All these experts in any domain, they are not used to work together with AI tools. So now if they are in the loop, how would their working processes change and adapt to such a scenario?